Hello, today I will be talking about timers, how to configure and use them. In simple words, a timer is a hardware that can count, and it can count up or down depending on the configuration, and it uses the system clock, where each clock step is considered a tick. So now let's configure and start using a timer. The first thing that we need to get is the base address of the timer that we are going to use. In this example, I will be using the timer 2. So here I have the base address of this timer. Also in this file, I have mapped all the peripheral and its base address. This information you can find in the reference manual, where you have all the base address of the peripherals available in the microcontroller. So all this information I have in that file. Another configuration that I have created is this structure, where it has all the registers that a timer can use. So these registers you can find in the reference manual again. So you can go to the timer 2 registers and register map. So each one of these registers I have mapped in here, and down here I have created the timer. So the timer 1 is of this type, and it starts from the base address of timer 1. The same thing for timer 2, 3, and 4. This configuration that I did for the timer, I also did for some other peripherals like the GPIO, the RCC, and the AFIO, which is the alternate function. Now we can start configuring the peripherals, and for this example, let's use the timer to make the LED on the board blink. The first step is to configure the port C pin 13, because this is the pin where the LED is connected. So here in this header file, I have defined all the registers that I need to use the GPIO ports. As you can see, I have the GPIO A to G. In this case, we are going to use the GPIO C. So we need to include this header file. So let's go to the main file and include the GPIO header file. Now let's declare a variable of this type. So it will be GPIO, and this variable will point to the same location as the GPIO C is located. We also need to use the RCC register, because we need to enable the clock for each one of the peripheral that we are going to use. So here I also have the RCC registers, and let's now include this header file too. Now let's create a point variable that points to the RCC address. So now we need to enable the peripheral clock for the GPIO-C. If we go back to the reference manual, we can go to the RCC register, we can go to the APB2 ENR, and here we can see that the port C is the bit 4. So we need to enable this bit. So back in the code, So let's use the RCC that we just created. Let's use the APB2ENR, and we need to enable the bit 4. The next thing to do is to configure the port C pin 13. To do this, we can go to the reference menu and we can go to the GPIO registers and go to the GPIO CRH. In this register, we can find the mode and the configuration for port 13. A good practice before setting any value in a register is to reset the value first. So first of all, let's reset the bits 20, 21, 22, and 23. So here we can access the register CRH and we can reset those 4 bits. Now we can start configuring the port. So let's go back to the reference menu and let's start configuring the mode, which is the bit 20 and 21. In the mode we have these options. Since the microcontroller that I'm using is only 8 MHz, I will use the option where we have maximum speed of 10 MHz. And let's access the same register, but now let's set the bit 20. We can set 1, and since the bit 21 is 0 because we resetted before, there is no need to set the bit 21 again. Let's choose the configuration. For this purpose, we can use the configuration general purpose output push-pull. To use this configuration, we must set in the bits 22 and 23 the value 0 and 0. But since we already resetted this value before, here in these bits we already have 0 and 0, so there is no need to set again. This is all the configuration that we need to do for the port C. Now let's start configuring the port B, pin number 3, which will be the pin responsible for the timer. So let's create another variable called GPIO B. To configure the port B pin 3, we need to enable the RCC for the port B, and also we need to configure the mode and the configuration. If we go back to the reference menu and we go to the RCC register and we can go to the APB2ENR, we see that we need to enable the bit 3 to enable the clock for port B. Also, we need to set the mode and the configuration for port B. Then we can go to the register CRL. The register CRL, we can find the pin 3. Here we have the configuration and the mode. So we need to use the bits 12, 13, 14, and 15. As the same we did before, let's use the mode as output mode, maximum speed 10 MHz, and the configuration, let's use general purpose output push-pull. In the code, we need to enable the peripheral clock for port B, so we can use the RCC APB2ENR, and we need to set the bit 3. Now we can set the mode and the configuration, but as we did before, first let's reset the values. So After resetting the values, now let's set the mode, which is the output maximum 10 megahertz, and the configuration is output push-pull, which is 00. But since we resetted the values here, we already have 0 in those bits, so there's no need to set. Using the port B, by default the port B pin 3 is not be used as a general purpose pin, so we need to use the alternate function to set this port as a general purpose. So to do this, we need to use the alternate function registers. If we go to the datasheet, the PB3 is using the functionality related to the JTAG. So we need to change this and use the remap options. To do this, we can go to the reference menu and we can go to the alternate function, and we can go to the alternate function registers, and we can go to the MAPR. Here we can see that the bits responsible for the JTAG configuration are the bits 24 to 26, which are these options here. So we need to disable the JTAG configuration. So to disable, we need to set this value 100. By doing this, we are going to use the PB3 as a general purpose. First of all, we need to go back to the code and let's create the variables related to the alternate function. As I showed before, I have the alternate function registers mapped in here. So let's create the variable. So first, before setting any value, let's first reset whatever values there in that register. And now let's set the value 100 in the MAPR register. Now that we have disabled the JTAG configuration, now we need to set to use that pin as a timer 2. So as you can see in the MAPR register, we can see that the timer 2 is represented by bits 8 and 9. If you go to the description of those bits, you can see that we can use the partial remap. By using the partial remap, we are able to use the PB3 channel 2 as the timer 2. So let's set this value. Another thing that we need to do before setting this value is to enable the peripheral clock for the alternate function. So to do this, we can use the RCC registers APB2 ENR and enable the peripheral clock. You can find this information in the reference menu. If you go to the RCC registers APB2 ENR, here we can see in the first position we have the bit related to the alternate function, so we need to enable this bit, and that's what we did when we enabled here. We also need to include the alternate function header, and now let's start configuring the timer. So let's include the header file. This is the header file of the timer. Here I have all the registers that I can use, and here I have created some macros. The timer that I will be using is the timer 2. So let's create. The first thing that we need to do is to enable the peripheral clock of the timer 2. We can go to the reference menu, the RCC registers, we can go to the APB1 ENR, and we see that the timer 2 is this first bit, so we need to enable. So let's back to the code and let's enable the APB1 ENR and enable the first bit. Now let's start configuring the timer. So we can go back to the reference manual, go to timer 2, and the first register that we can configure is the CNT, that is the counter value. So let's initiate the timer with a value 0. Let's configure the timer to count in milliseconds. So if I have 1000 milliseconds, I have 1 second. To achieve this, we have to use the prescaler register. This register is used to divide the clock frequency. So as you can see here, it says that the counter clock frequency is equal to the frequency divided by the prescaler. So we know that the 8 megahertz in 1 second, we have this value. But we want this value to be 1000, because we would have, for 1 second, we would have 1000 ticks of clock. So, and this is exactly 1 second. So to do this, we need to take this 8 megahertz and divide by 8000, then we get 1000, or 1000 ticks of clock. So in the prescaler register, we pass 1000. Let's go back to the code and let's use the prescaler registers, and let's set 1000 minus 1. We need this minus 1 because it starts from 0. Now we need to set the value that we want to count. For example, if I want to count until 10, I set the value 10. So we need to use the ARR register, and let's say that I want to count until 1000, which is 1000 milliseconds, or 1000 ticks, which is 1 second. Now we need to reinitialize the counters and apply these changes. We can do this by going to the reference menu, and we can see that the EGR register bit 0 is responsible for this. We need to set 1 to reinitialize the counters and generate an update of the registers. So let's set this bit. So now every time the counter starts counting and reaches the number that we defined in the ARR register, it will generate an interrupt. So when this interrupt is generated, we know that we reached that value. So first, let's clear this interrupt. If we go to the reference menu and go to the SR register, we can see that when this bit is set, an update interrupt is pending. So let's clear this bit. And the next thing that we need to do is to start counting. So to do this, we can go to the reference menu again, and we can see the CR1, and we have the CEN bit, which is the bit 0. Then we need to set to start counting. now that the timer is now counting, we need to know when the counter reaches the value that we defined. To do this, we can keep checking the bit 0 in the SR register. When this bit is set, it means that the timer reached the value that we defined. So we can write while we don't have that bit set, we can still run it. Once we reach the value, we can start to do another thing. So let's make this part of the code as a function. Let's define this here, and let's call this function as delay. And let's set the time we want to count, let's say in milliseconds. So in the ARR register, we pass the value that we are passing in the parameters. So I can call the function delay, let's say 1000. So it means that I will be trapped in this delay 1 second. So now let's test it. Let's put it inside the while loop, and let's turn on and off the board LED. So to do this, we use the ODR register. We can just simply flip the value that is in that register. So now let's test it. Let's flash the microcontroller passing 1000 milliseconds. As you can see, the LED is blinking. So let's change. Let's say that now I want 500 milliseconds. So let's compile. Let's flash. And you can see the LED start blinking faster.